Yeah, I thought it was. It's a little small on my screen, which is crazy because my screen's like that big. So, anyways, it is 5:30, and we did finish chapter 4 last time, and we're sort of already into chapter 5 just by the various conversations we had and stuff like that. But I noticed, of course, on the syllabus, we're supposed to finish chapter 6 by the end of this week, and that makes it problematic because online test 3 is supposed to be on chapters 1, 2, 3, 4, 5, and 6. And obviously, that means if I don't get chapter 6 finished in a reasonable time, I may need to go ahead and push the due date back on the online test 3. Of course, online test 2, which covers 1, 2, 3, 4, that's already due on the 17th. And of course, we've more than done enough for completing that in terms of chapters 1, 2, 3, and 4. So you guys are good to go on that. Uh, just keep in mind that I may change those due dates, and I'm not sure that I'll take time to go out and change it on the syllabus. I'll just be doing it verbally and or email wise. But of course, if you're subscribed to, well, in some sense, there's there's various things you can do to have Canvas notify you whenever any changes occur. And if you're set up in that system, when I change due dates on Canvas, they should give you an email to remind you of that. That's somewhat what I'm relying on, but I also try to either make an announcement or try to make an email. So just keep an eye on that, and just know right now that I'm warning you that there's a good chance that practice test three, or excuse me, online test 3 may be moved back because I don't want to do online tests except every 2 chapters. So test 1 is chapters 1 and 2. Test 2 is chapters 3 and 4. Again, all my tests are comprehensive, so even if test 2 is chapters 3 and 4, chapters 1 and 2 are part of it. And then test 3 has to be 5 and 6. But again, that means 1, 2, 3, and 4 are still part of it. So I will be trying to assess that and make a decision as soon as possible. But let's see what we can get done today. I'm going to go ahead and share my, well, actually, before I do that, I was going to go ahead and share my screen with you, but I needed to give you a little introduction to friction. And sadly, I don't have exactly the best setup to do this because I haven't learned enough about Zoom to and my Mac computer system to fix it so that my camera could be directed at a lower surface and then not move every time I move. See how the camera's moving when I move. There's probably some setting. I don't know if it's a setting in Zoom or if it's a setting in my Mac or whatever, where I can get it to stop doing that. But mostly it's something I like, so I don't necessarily want to do it except for this presentation. So instead, what I'm going to do is I'm going to imagine my hand as a tabletop. I've done it 2 or 3 times already in the course, so I'm going to do that now. So if you look, my calculators, like most people's calculators, they have these little feet on them, especially with the big screen slash graphing calculators. They have these little rubber feet on them, and those are really good in showing you the essence of friction. If you don't have those little rubber feet, it's still the facts about friction are still true. It's just harder to see it unless you've got those nice tacky little rubber pegs or nipples or feet or whatever. So what you can imagine is my hand is a tabletop, and what I want you to think about is, and more than think about, I would like you to lay your calculator or something that is not easy to slide along the surface of your desktop, preferably something that's not all that easy. And what I want you to do is think about pushing a little bit to try to make the object move. I think when you do that, you're going to discover exactly what I'm trying to teach you. Specifically, and I'm saying this slowly so that you can have enough time to try it. So I'm hoping people are taking their calculators and laying them on the desk with the rubber sides down, and they're slightly giving them just a finger push and seeing that nothing moves, and then a little harder, and then a little harder, and then a little harder, and then a little harder until it actually moves. And then I want you to try to continue pushing it along just a little time and see what it seems like the forces are doing. Okay. I suspect some things are going to happen that are very specific and are a reflection of the reality of the physics of friction. And hopefully I've done that. So now that I've taken all this time stalling, trying to make sure y'all had an ample opportunity to do this, I'm going to go ahead and explain what happens. So what normally happens is when I push a little bit, friction kicks in, and friction is sort of you can think of it as something that tries to stop relative motion. So, for instance, when the calculator is on my tabletop, if I try to move it, then that's relative motion between this surface and this surface, which is supposed to be the desk, of course. And friction generally tries to stop two adjacent surfaces from moving relative to each other. What I'm suggesting is you're going, when you go to push on this, you're going to feel a little bit of force. And what's happening is you're applying a force and friction's responding in some sense as if it's, a sentient being. It's responding in some sense in a way that it's trying to fight you and the force that you're applying. And if you push a little harder, it'll do the same thing. If you push a little harder, it'll do the same thing. And if you push a little harder, it'll do the same thing. If you keep doing that, eventually you're going to find a force at which you can apply, or a force that you apply that the friction can no longer stop. So it's as if there's some maximum amount of friction that the universe can muster when you're trying to push your calculator along the surface. But the other part of the observation that hopefully you guys will see, and again, it really is critical for you to sense this other part. It's critical for you to have these little rubber nipples or something that has some kind of traction. But what you should discover is that yes, if I put a small force, friction stops it. If I put a little bigger force, friction stops it. If I put a little bigger force, friction stops it. And when I'm saying stop it, I mean it's just keeping the object from moving. But if you keep on doing that and increasing the force, again, eventually you get to a spot where friction will not stop it, and in fact, it starts moving. And then immediately you'll notice that your hand no longer has to apply as big a force as it did to get it started. So it's like the friction keeps applying more and more force in response to more and more force that you add up to some maximum. Once it reaches that maximum, then for some reason the friction force drops. Okay, that's the observation that I hope all you are seeing. Did anybody try that? And more specifically, did you try it and get the results that are consistent with what I just said? Y'all can type that or say it. Either one's good for me. Thank you. Oh, by the way, is it Eli or Ellie? I don't know. I'm still an idiot about that. All right, and yes, Hope saw it. Good job. So, anyways, that is Eli. Okay, gotcha. Again, hopefully that's right. Did I say that right, Eli? Or is it Eli? No. Yeah, okay, yeah, cool. All right. Sorry about that. Just an ongoing thing in my head that I've been working on. All right, so what Eli and Hope did notice is actually correct. So now I'm going to give you an explanation of that, and your book does the same thing, but I'm going to give you an explanation in equation form. And in order to do that, I'm going to have to share my screen, and here I go. Here I go. Here I go. Here I go again. Oh, yep. I just went into some. What is that? What are those people? Salt and pepper. That's who that was. Here I go. Here I go. Here I go again. Or is that not salt and pepper? I don't know if that is. Waiting, waiting, waiting. Okay, so this is something that's important, but I'm going to push it to the side to get started with this friction stuff that we were just talking about. So there's actually multiple types of friction, and the two types of friction that I'm talking about right now are what we call static friction and kinetic friction. So static friction is the friction that exists between two objects when they're not moving relative to each other. So for instance, when I was doing this with my hand, there exists a friction force between the plastic, or more specifically, since my little rubber nipples are working, there is a friction force between the rubber and my skin. If you had your calculator laying on the table, that friction force is between If you had rubber skids of some sort, it's between rubber and whatever the material your desktop is. And those are the two relevant parameters, is what is the material of the two things that potentially can slide on one on the other. Okay. That motion, that friction that occurs when the objects are not moving is called the static friction. And then once it gets moving, it converts to what we call kinetic friction, and kinetic means motion. So that's the friction when two surfaces are moving with respect to one another. So what we do to specify what you just observed is we say that the static friction, and we normally use like a script F, like you might recognize as the F that was used in your algebra, pre-calculus classes for functions. So it's F sub S, which means static, is less than or equal to. And now this is where I'm going to come in and tell you it's directly proportional to the normal force, which I've already been telling you. Okay. But the constant of proportionality is what we call the coefficient of static friction. So my constant of proportionality is this mu symbol with the subscript s, because there's a mu for static friction called mu sub s, and then there's a mu for kinetic friction called mu sub k. Mu, the Greek letter mu, is the same as the symbol that we use for both of those coefficients of friction. And in fact, in chapter 5, you'll see a table in your textbook that has some common kinetic friction and static friction constants or coefficients. Now, I said it was proportional to the normal force, so you might choose to write this as just N. I'm going to write, oops, I am going to write it as the normal force. Okay, notice that's not a vector equation. A vector equation, if I had a vector symbol over the F sub S and then another vector symbol over the normal force, then that would suggest that the friction force, the static friction force, is less than or equal to mu static times the normal force. But it would also say that the static friction force is in the same direction as the normal force, and that's not true at all. So that's why we don't do that. But notice by saying the friction force, the static friction force, is less than or equal to mu static times the normal force, that allows whatever force you apply to the calculator, for instance, you allow that friction force to exactly meet that force up to some maximum. So in other words, as long as the force that you're applying with your finger is smaller than the static coefficient of friction times the normal force, then the friction force will be big enough, and it just keeps it moving from moving. And when you increase that force a little bit more, if it's still less than mu sub s times the normal force, then it's still up to the task and it keeps it from moving. But if you ultimately reach that mu sub s times the normal force, then at that point it's still not moving, but even a infinitesimal bit more force will immediately cause it to start moving, and then it's going to kick in such that the kinetic friction is going to be active. The formula for the kinetic friction is friction kinetic is equal to mu kinetic times the normal force. So those are our two formulas, and you can sort of look at it. I think your book does a graph like this, which is pretty helpful. Uh, but what you can do is you can look at, say, the force applied versus the, ooh, I lost about where I was. We can look at, for instance, the force applied versus the friction force. And when we do that, you can get a sort of nice little graph, and the graph is shown in figure 5.3. So if you do, this is the friction force, F. Notice I didn't put a S or a K on it because it's the friction force, and that includes the static friction force plus the, and I don't mean plus in terms of addition, but it includes the static and the kinetic friction force. And then this axis represents F applied. And that it would be in the case of your calculator and your finger, that's the force applied by your finger. Now, what happened was basically for each force that you applied, the friction force was able to counter it with by supplying exactly the same force. So that, for instance, if you did 1.0 newtons, both of these would be measured in newtons, by the way. If you applied a force, for instance, of 1.0 newtons, then the friction would supply a force of 1.0 newtons as well. And that continued on until you got to this quantity right here, which is mu static times the normal force, at which case it drops back down and the friction force stayed at this quantity. Now, this quantity is mu kinetic times the normal force, and I've drawn that so small it's not very helpful at all. So I'm going to zoom in a little bit and better show what I'm talking about for this particular application. So I didn't draw these lines too well either, but when the drawing was that small, it didn't matter too terribly much. So, oops, I didn't mean to erase that. So this force is mu static times the normal force. This level of force is actually mu kinetic times the normal force. And all the other forces, of course, is just going to be exactly the same up until you get to this point right there. From that point to the right, any force you apply is only going to be subject to the static coefficient of friction and therefore only the static force or the static friction. And therefore, it's going to be a fixed amount mu kinetic times the normal force. As I said, there is a table. The table is table 5.1, and some examples they gave you for the coefficients of friction. Wood on wood has a static coefficient of friction of 0.4, but it has a kinetic coefficient of friction of only 0.2. Ice on ice has a static coefficient of friction of less than 0.1, but ice sliding on the ice has a kinetic, notice I said the word sliding there, that's because I'm talking about kinetic friction. So ice has a static coefficient of friction when it's sliding of 0.03. Metal on metal, if it's lubricated, has a coefficient of static friction of zero point 0.1, but zero point 0.07 for kinetic. And steel on steel, unlubricated, in this case it's a very specific metal, steel, and it's unlubricated. In that case, the friction force is zero point 0.7 static and zero point 0.6 kinetic. Rubber on dry concrete, in that case, they're essentially the same. They're zero point 0.8 in both cases. That's sort of the aberrant behavior in general. And I'm going to write this here. In general, mu static is greater than mu kinetic. And that's a big philosophical and physics concept. It's the very reason, for instance, if you've ever lived in a snow-prone area, or if you've ever done any, let's say mud track racing or ice, racing on ice, like with cars or bikes or something like that, you've probably learned it a little bit already. But if you lived in that snow area, the most obvious example showing this was when your meteorologist on an upcoming storm was trying to teach you how to deal with sledding on the ice, and they specifically told you that when you encounter a patch of ice and you go into a skid, you're supposed to turn into the curve. Okay, I'm going to draw a picture real quick to give you some sense of why that's the case. So if you imagine this is a curve and you imagine it's a icy, snowy day and this is the car that you're riding in, you could say, for instance, here's the tires. Obviously, most cars have their back tires in such a way that they don't turn, but this is a slight turn that we're going around. So I tried to put the front two tires slightly turned so that you can see it's trying to make the turn. The car is in fact going this way, but the car driver's intent is to follow this dotted line along the curve. As the car goes around the curve, though, it's very possible that the car will begin to slide, excuse me. The car will begin to slide like this, in which case the back tires, of course, are still parallel to the car, but the front tires, which were turned a little bit this way, just to show they were trying to turn to the right, and I drew that a little more turned than I really meant to, but I was just doing it to make sure you could see that they were turned to some extent. So let me draw it a little better now. So if this is how your tires were turned, then what's just happened is your car slid from going straight ahead such that the back end slid out to the left. So if you're in the driver's seat right now, your back end sliding around like this. Okay? Everybody see that? Does that make sense? Now, what the meteorologist tells you is turn into the skid. In this case, you are skidding this way. And I'm going to draw this, try to make it obvious. I'm going to draw it with this green pen. So that's your skidding direction. You're skidding to the left. What the meteorologist is trying to teach you is that when you're skidding this way, you are trying to turn into the skid by turning your wheels such that they point this way. So notice how those wheels are now, at least in the front, the wheels now in the front are essentially parallel to the dotted path that we were trying to ride along. Okay. I need to reiterate that this was the initial velocity, that when I drew that green arrow, it obscured it a little bit. But that red vector shows the direction that the car was going initially. The car is still trying to go that direction, but now the driver has turned into the skid. And the reason why that is the appropriate decision is this. If your tires are as they seem here, notice if these tires actually rotated, if they rotated this way, they're not going to be able to align themselves such that they could regain or rotate in the direction that the car is actually moving. The car is moving this way, and the wheels are turned almost perpendicular to the path that the car is going along. So there's no way spinning is going to sort of match the speed of the car. But if you turn your wheel to the left, as we've done in this last diagram, you could see that if the tires actually rotate in the same direction they were rotating when you drove into the skid, meaning forward, basically, like the front of the tire is going down, hitting the road right at the bottom of the tire, and then going up and reaching the top, and then going down to the front again, so on and so forth. So if it's doing that, then you've actually got your tires aligned in such a way that static friction could kick in. Because what ultimately happens when you're driving a car, unless you're skidding due to slamming on the brakes, or unless you're spinning out due to slamming on the accelerator, then normally the tires and the road and the velocity of the car are all matched in such a way that the very bottom of the tire doesn't have any relative velocity with the ground under it. So normal driving, there is literally no motion no motion of the bottom of the tire relative to the ground, at least horizontally. What you do know is as soon as that bottom part of the tire is on the ground, a split second later it starts to turn up like this, as because it was going like this, right? So when it gets down to the bottom, it's level and it's at the very bottom, but a split second later, it's moved up and it's no longer at the very bottom and it's in this position. So there is some motion vertically, which is perpendicular to the road, but there's no motion parallel to the road. Because of that, we know that the very bottom of the tire, again, unless you're skidding due to slamming on brakes or spinning out due to slamming on the accelerator, we know that the velocity between the bottom of the tire and the road is zero. Because it's zero, that means the normal driving condition is the bottom of your tire experiencing static friction with the road surface. So that's why you actually turn into the skid, which means in the case of the steering wheel, if we were to look at the steering wheel right here, let's see, this is your steering wheel, and maybe you have one of those three-prong steering wheels or something like that. If this is your steering wheel, what you did to turn into the skid was turn the wheel this way. And you don't want to go too far, obviously. Going too far would sort of self defeat. But you also don't want to go not far enough because if you turn your wheels just a little bit, then they're not going to align either, and still they can't regain static friction. So the whole purpose of turning your tires into the skid, and again, I mean turning your steering wheel the direction that your back end is sliding out from under you. When you do that, you actually have your tires, if you don't go too far before doing it, you have your tires going parallel to the path that your car is sort of coasting in, and they can regain static friction. And by regaining static friction, you then again have control. The kinetic friction being so much smaller than the static friction is the reason why this is the proper protocol when you get in a skid on ice. Does everybody understand that? Does anybody have any questions regarding that? Okay, so that's a big concept. There's two things that work here. The big physics concept is that generally speaking, static friction coefficients are larger than kinetic friction coefficients. Drop my pencil. Sorry about that. So the general physics principle here is that static friction coefficients are generally larger than kinetic friction coefficients. Of course, in your book, at least to one decimal place, they show one example, rubber on dry concrete, where the static and kinetic friction are exactly equal. This table is also what the author expects you to use in his online homeworks as well as the homeworks that appear at the end of the chapter. So if they ever ask you a problem to solve a problem involving friction, and they tell you what the surfaces involved are, they're expecting you to come back here to table 5.1 and look up the appropriate friction coefficient for those particular surfaces. Any questions on that? All right, I'm still going to save this page right here, which is introducing chapter 5 using Newton's laws, friction, circular motion, drag forces. This is all about the circular motion, and this is a specifically a exercise that I would like you guys to try so that you'll better understand. Basically, it's a centripetal acceleration formula that we're going to be using over and over again. Okay, we're not to that part yet though, so I'm going to come back and hit that later. I just wanted to have it written so I could explain it without having to write all those sentences in real time. So now that I have this, let's look at some different problems. Your book, for instance, has a example 5.1 that's way more work than actually than it's worth for me copying it. So what I'm going to do is stop sharing, and then I'm going to share that particular image, which is potentially a copyright violation. Oops, wrong one. Potentially a copyright violation. So I'm only going to do it for a little while. I don't. Well, it probably there's probably no way around it. It's definitely copyright violation, but here we go. Example 5.1, it says friction, static, and kinetic. A 10 kilogram box rests on a horizontal floor. The coefficient of static friction, mu static, equals 0.40, and the coefficient of kinetic friction, mu kinetic, is equal to 0.30. Determine the force of friction, F friction. Notice your book's using different terminology than I use. I usually use the script F instead of a F with a subscript friction. But it says determine the force of friction acting on the box if a horizontal applied force FA is exerted on it of magnitude 0 for part A, 10 newtons for part B, 20 newtons for part C, 38 newtons for part D, and 40 newtons. This is a really a good problem because it expresses exactly the points that I've been trying to make with this. So example 1, what I'm going to do with this example is we know the mass is 10.0 kilograms. It's on a horizontal floor, and we just spent all of last class learning that as long as the surface that something's sitting on is perfectly horizontal and no additional forces are pushing down on the object or lifting up on the object, then the normal force is exactly equal in magnitude to the weight. So that also tells us that the weight is equal to 10.0 kilograms times 9.80 meters per second every second, which is obviously equal to 98.0 newtons. That's the weight. So the static friction, F static, has a max value, so I'll label it max because remember it's a less than or equal to statement. It has a max value that is mu static times the normal force. Notice I switched back to using F with a subscript N. That's pretty normal for me, so keep up. Capital N is probably going to mean normal force, but sometimes I'll write F with a capital N as a subscript, and that also means normal force. We were told that mu static was equal to 0.40 and that mu kinetic was 0.30. So in this case, it's 0.40 times the normal force, which is the same as the weight. Please make a note of this in words, okay? If you look back at your notes and you see that I calculated weight equals 98 newtons, and then I just plug that in here, you might think in the future, oh, okay, so the static force is just, or the friction force is just the coefficient of static friction times the weight. That's not true at all. It's times the normal force, but I pointed out to you that when the floor or the surface that it's sitting on is perfectly horizontal and no additional forces are pushing down on the object or lifting up on the object, then the normal force is equal to the weight. That's why I'm using 98.0. It's not that the weight is the appropriate formula. It's that the normal force is equal to the weight in these special cases. So I've got 98 times zero point 0.4, and that gives me 39.2 newtons. Now, technically, that's 39.2, but the 2 has an underbar because it's not a significant figure, specifically because the 0.40 forced the number of sig figs to only be 2. I can also calculate the kinetic friction, F kinetic, but that's a constant. That's not one that changes like the static friction does. In this case, it's mu kinetic times the normal force, which is 0.30 times, again, the normal force is equal to the weight for this type of setup. So that's 98.0 newtons. 98.0 times zero point 0.3 is equal to 29.4 newtons. And again, that 4 is not a sig fig. So now that we have that, we know what the forces are. So when they say I'm going to draw a picture of the situation that we have here. What we have is a 10.0 kilogram box sitting on a surface. We have acting on it a weight equal to 98.0 newtons and a normal force, F normal, equals 98.0 newtons. And we have, in addition to all this, actually, I should probably do purple. It looks like I'm calling purple the positive direction vector. So I'm going to say right is positive, even though we're not really doing anything that requires us to make such a call. But the key thing here is this is F sub A that they're referring to. So for part A of the question, FA is equal to 0 newtons. And what they're asking for is determine the force of friction. So when the force on it is 0, the force of friction has to be a static friction force, and it's equal to 0. Because remember, the graph up there shows that the force you apply is equal to the static friction up to some maximum value. So 0 is clearly way below that maximum value, so the friction force is going to be 0. For part B, we have FA is equal to 10 newtons. So in this case, the friction force, again, remember they're asking for the friction force and all of this. So, oops, there I go. They're asking for the friction force from all of this, and my Newton is looking really bad. So, anyways. So in this case, the 10 newtons is again smaller than the max friction, the max static friction force. So the max static friction force is what happens. And in this case, it'll be a static force and it's equal to 10 newtons. So I guess I should draw it this way just to show you what we're talking about. You can look at it this way. This is the friction force, but notice I had to write that F. I didn't put a subscript S and I didn't put a subscript K on it. That's because for various forces F sub A, the friction force can be an F sub S or a F sub K. Right now, we're still in the F sub S range. The next part is part C. And for part C, actually, for part C, they said the friction, the FA was 20 newtons. And what that means is, again, the FA is smaller than the max friction force, the max static friction force. So the friction force will be a static friction force, and it will be exactly equal to FA so that the object doesn't move. For part D, FA is equal to 38 newtons. You can see it's getting really, really, really close to the maximum static friction force, which was 39.2 newtons, which we technically have to treat as if it was 39. But either way, it's still less than 39. So the friction force will be static, and its value will be 38 newtons. Now we get to C, which is FA equals 40 newtons. What's going to happen then is now the FA exceeds the static friction force. The static friction force can't be any higher than 39.2. This is higher than 39.2. So if you look again, like on that graph up above, you can see we're in this area, so all the friction force is going to be the kinetic friction. So I'm going to say the friction will be kinetic, and in this case, it's going to be 29.4 newtons. So these are the answers. Does that make sense to everyone? It's not enough bang for my buck for me to copy all those words down, but it's certainly a wonderful problem to express exactly what happens with friction forces when they're applied to objects. No one has any questions on this? All right, I'm gonna open up the chat just in case someone's right there. Uh-oh. All this time I've been here and I didn't switch back to my iPad. Oh, God. That's terrible. Did y'all see the... Okay, this is bad. Let me go ahead and stop this sharing. We've got this, and I completely forgot to share that. That's not good. Anyways, let's go ahead and share the appropriate screen since I'm obviously a goober. So I'm doing my iPad now. And I've done all that more or less for nothing, but let me go over it again. Y'all should remember the question now that I've recited it. Feel free to speak up. That was really bad of me, and I'm not saying it's your fault, obviously. It's clearly my fault, but feel free to speak up. Some of y'all might not have speakers. Maybe that's why. Or maybe you did speak. I just didn't hear it. Did anybody actually try to speak? Okay, I don't see any notices about that. But I do now have, and now the darn chat left again. Okay. Sorry about that, Beth. Good gosh, you did that at 6:09, and well, at least it's only 3 minutes since then, or 2 minutes since then. All right, so this is what I actually wrote. This area right here is what I was doing with regards to that problem. So they gave us the mu static was zero point 0.4, the mu kinetic was zero point 0.3, the mass was 10 kilograms, and of course we know weight is equal to m times g, so that's what I calculated here. That gave me the weight being 98.0 newtons. I made the argument, this part's important. I made the argument that when an object rests on a perfectly horizontal surface and the object doesn't have any additional forces being pushing down on it or lifting up on it, then the normal force is just going to be equal to the weight. And that's what we have in this problem. So if you look at the free body diagram that I have here, you can see that the weight is always 98.0 newtons. And since FA is going to be applied horizontally and the friction force is always slash anti-parallel to the motion, and I say slash because it's sort of, you can think, I want to say parallel, but it's technically the opposite direction of the relative motion. So that's why I was trying to say slash, because I wanted you to think parallel slash anti-parallel. And the normal force, of course, is normal to the surface, and that means it's normal to the surface. So if you just set up a summation of forces in the y direction equals mass times acceleration in the y direction, and realize that for this problem the acceleration in the y direction has to be 0, then you get F normal minus W is equal to 0, so F normal is equal to W. So that's actually what I'm using in all of this. So now that I know the normal force is exactly 98 newtons, then the maximum static friction force would be the mu sub s times the 98.0, and that gives me 39.2. The kinetic friction force is always a constant mu static, or excuse me, mu kinetic times the normal force, which is 0.30 times 98.0 newtons, and therefore gives us 29.4 newtons. So when we applied a force of 0, if I look up here, the 0 force corresponds to a 0 friction force. So I wrote the friction force will be a static friction force, and its value is 0. When I do part B, where FA is 10 newtons, the 10 newtons is still smaller than the 39.2. So this being like the 39.2 in this case, I'm like over here at some force smaller than the 39.2. So the FA is just going to force the friction force to be equal to itself. So the friction force is 10 newtons when the FA is 10 newtons. When the FA is 20 newtons, again, that's less than the 39.2. So the static friction will reply again by doing exactly the same force. So the static friction is the friction force that's engaging, and it's only 20 newtons. When they go up to 38 newtons, they're getting closer. They're like right here. But again, they're not there, so it's still less than the static friction force maximum. And in fact, it's exactly equal to the applied force. The applied force is 38 newtons, so the friction force will be a static friction force, and it's going to be 38 newtons. And then finally, when FA is 40 newtons is greater than 39.2. So we're in this region right here. That region right here, we go up and the friction force is exactly equal to mu kinetic times the normal force, which we found was 29.4 newtons. So hopefully y'all really understand it now that I explained it twice. Sorry about that, everyone. Anybody have any questions on that? Okay, so that is a very good and typical problem that every student should be exposed to at least. But now we're going to go ahead and move along. There's a good conceptual example, and I'm going to give you a quick version of that. It says a box against a wall. You can hold a box against a rough wall and prevent it from slipping down by pressing hard horizontally. How does the application of a horizontal force keep an object from moving vertically? So that's a good point, and it's also a good point that you sort of need to understand that everything we learned about vectors says that when a vector is applied, a force vector is applied to something, it can only act in the directions parallel to the vector. But in this case, we have something that sort of contradicts that. So you have a box right here, and you have a wall, and what the box has is a specific weight. W is equal to m times g because the box has a mass of m. Now, when you push on this box, oops, I should probably use a pen instead of a laser pointer. But when your hand pushes on this box to the right, then you get a force, which I'm going to call right as positive, so I'll use that as a purple arrow. Then you get a normal force that acts in the what I would call the negative x direction, and that would be F normal like that. But you also have a friction force that, because gravity is trying to pull the box down, the friction force therefore acts in the upward direction, which again is another positive direction. Oops, I just was supposed to draw that normal force in red. I did not do that. Let's do that real quick. So this normal force is that way, but the friction force is right there. And since there's no motion right now between the wall and the box, that friction force is a static force. So by pushing the box against the wall, you're supplying a normal force that would otherwise be zero. When you push with a force of zero point 0.1 newtons, the normal force is going to respond and be zero point 0.1 newtons, assuming the wall can sustain zero point 0.1 newton force. If you jump it up to a half a newton, then assuming the wall can sustain the half a newton, then it's going to push back with a force of half a newton. So summation of forces in the x direction equals mass times acceleration in the x direction, which again, in this case, it's the x direction that's clearly has no acceleration. So we're going to get from that minus, f minus f normal is equal to 0. So you see that the normal force is in fact equal to whatever force you apply. Now, in the y direction, the summation forces in the y direction equals mass times acceleration in the y direction. Ideally, we want the acceleration to be zero, but we can leave it as just ma and then know that once we got all the equilibrium conditions met, then we can just figure out what happens when a equals zero. But right now, I'm just going to say the only forces in the y direction we have are the friction force Fs minus the weight. And remember, I told you once I started in the next chapters, I would start writing the summation of the forces as number minus number plus number. In other words, I'm not going to take the time to write a plus symbol and a minus sign every time. I'm just going to write subtraction. So in this case, the static friction force upward minus the weight downward is equal to the mass times the acceleration that it is going to experience. In this case, if we want it to accelerate, if we want it to experience no acceleration, then we would need the static friction force to be equal to the weight. So if F static equals W, then A is equal to zero. But remember, F static is less than or equal to mu static times the normal force. And since the normal force is equal to the force you apply, the friction force is mu static times the force you apply. So you can now see that if I supply a large enough force horizontally, that can cause a large enough uh, normal force from the wall that creates a friction that's large enough to keep the box from sliding down. Any questions on that? Example 5.2 is what that was. So no questions? All right, so let's consider another problem. And a lot of these problems I can actually do without any wording, so that's why I'm not too worried. Like normally I try to copy a bunch of questions down before lecture and have them written, handwritten first, or sometimes I'll try to type them in. As you can tell, that's a pain in the butt, a lot of work, especially when I can't find. My wife was kind enough to buy me an actual keyboard to use on my iPad, but I haven't been able to find it since she bought it for me because we were having a lot of stuff going on. So, anyways, let's look at another example. So, in this case, what I'm going to say is we're going to have a box sitting on a perfectly level surface. I'm going to say this box has a mass of 15.0 kilograms and it's sitting on a horizontal surface. And I'm going to say that I will apply a force, and that force is not going to be perfectly perpendicular, nor is it going to be perfectly horizontal. That force is going to be, in fact, at a 30.0 degree angle, and its magnitude will be 42.0 newtons. I'm going to say that we have a kinetic coefficient of friction of zero point 0.3. So let's say mu kinetic is equal to 0.30. And what we'd like to know is what is the acceleration? So now you might think, wait a second, uh, they didn't give us the the static coefficient of friction to be sure that we're bigger than that. Well, this example that I drew is one like the one that the book worked out, but in the one the book worked out, they had already worked out that the forces I'm applying are larger than the static friction. So we go on the assumption, and I don't know why I all of a sudden wrote that in non-cursive, but assume FP is large enough that F static. Ooh, I should write it as a script F. As is large enough that the static friction force has been exceeded. So I'm using basically the fact that this example was done before, and they already showed that the force was sufficient to overcome the static friction, and therefore I know the active friction force that's going to occur is going to be the kinetic friction. So now all I have to do is solve the problem. So I'm going to draw a free body diagram, which is something you should try to do every time you apply Newton's second law of motion. So I'm going to draw a free body diagram to represent the system. I'm going to say the right is the positive x direction, and to the upward direction is the positive y direction. I'm going to uh, claim that the box is this purple dot right here, and the mass of this purple dot is 15.0 kilograms, like that. Now, the forces acting on it are, oops, this stupid program, it's really bad how it just automatically changes to random stuff. But this force is 42.0 newtons, and it's at 30.0 degrees. Notice I drew it purple. I'm going to use red and blue to represent positive and negative anti-respectively. Red's going to be going to be the negative direction, and blue's going to be the positive direction. So the fact that this isn't aligned along either axis means I should draw it some color other than red or blue. So the other forces we have acting on this object is, of course, the weight of the object. And the weight of the object, W, is equal to M times G. And that is 15 times 9.8 meters per second. And that gives me 147 newtons. There's also a normal force, and this one acts upward, and I'm calling it F sub n. And then in addition to that, there is a force that acts in the negative x direction. And in this case, that force, I'm going to draw it over here to the left in a way that I don't normally draw. I usually like the arrowheads to land actually on the object that they're applying a force to. But in this case, I'm drawing it to look like it's pulling the object, and that's acceptable. So this friction is, and I wrote static, I meant kinetic. So that force is the kinetic friction force. Now, that's all the forces on the body, but I'm still not ready to do anything because I haven't rendered that purple vector into components that are parallel to the x and y axes. So I'm going to go ahead and write down my trig functions as I advised you guys to do to make sure you are properly learning how to break down vectors. So first off, I'm going to write the sine of 30.0 degrees is equal to opposite over hypotenuse. There's my opposite side, which obviously points in the positive y direction. And here's my adjacent side, which also obviously points in the positive direction. But this is going to be opposite over hypotenuse from so in SOHCAHTOA or from some old horse. And the opposite, of course, is the uh, F sub y, and the hypotenuse, of course, is 42.0 newtons. This means F sub y is equal to positive sine 30 times 42. So if I take sine of 30, which you know is a half, and multiply that by 42, you get 21. Yeah. Similarly, we can do cosine of 30.0 degrees, and that's adjacent over hypotenuse, which gives us F sub x over 42.0 newtons. that means F sub x, which again, I'm forcing the positive sign, is going to be 42 times cosine 30. And that gives me 36.3 or 36.4 newtons that way. Okay. Now I've got these forces. This one is 36.4 newtons, and this one is 21.0 newtons. Now I can use Newton's second law of motion, the summation of the forces in the y direction equals mass times acceleration in the y direction. But we know this is a case where the box might slide left and right, but it's never going to slide up or down or dig into the surface or jump off the surface. So the position, the y coordinate of this object is always going to be a constant, and that makes the force, or excuse me, the acceleration equal to zero. So in this case, what we end up getting is the normal force, F sub n, minus, well, actually, let's first off say plus 21.0 newtons, and then say minus 147 newtons. All of that has to equal zero, and therefore I can solve that for the normal force, and the normal force is going to be 147 minus 21, which would be 126. So the normal force is 126 newtons. That's what we got for from Newton's second law in the y direction. Now we can apply Newton's second law in the x direction, and this is where we're going to calculate the acceleration. Normally I'd put a subscript x on that, but that really is the only acceleration, so why waste the time putting an x on it? The forces acting in the x direction, of course, are the 36.4 newtons, which is acting in the positive direction, minus, remember it's plus a negative, but minus the friction force, which in this case is the kinetic friction. So we're going to say mu kinetic times the normal force, and then all that's going to be equal to 15.0 kilograms times A. So now I can go ahead and plug these numbers in. I'm going to get 36.4 newtons minus, now I'm going to take the 0.30 and multiply that by 126, and that's going to give me 37.8 newtons. Whoa. By me choosing a number off the top of my head in an attempt to avoid copyright issues, I've made a problem that was a little bit of a problem. Specifically, I've made a problem whose friction force is actually too small, or excuse me, whose friction force is too large, or whose pushing force is too small. So, what we can do is say we can say that basically, since the force is smaller than the friction, than the kinetic friction force, then it's not going to move at all. Okay, that's actually the right answer if these were the numbers. Okay, now what I can do is go back and do the same thing, but do it with slightly different numbers and get a different result. But let me go ahead and finish this one. I'm going to say since F sub x is less than the kinetic friction, the box still cannot move. Now, whether or not such a value of coefficient of kinetic friction exists so that you could actually apply a force that's bigger than the static friction force, but come up and that it still be smaller than the kinetic coefficient of friction, that's probably non-existent. But still, that's what you'd have to conclude if such a problem happened. Now what I'm going to do is we'll work another example, which is going to be more or less the same, except I'm going to change the numbers so that we get better results. And that'll actually be okay because we can do this rather quickly since we've done all the work. So I'm going to say copy this, and we'll call this example 4. That's all because I tried to avoid it, and I put a little bit of force up, but I just didn't do enough. So that was my fault, obviously. Let's say example 4. So now what I'm going to do instead is I'm going to change this force from 42 newtons to 50 newtons, and I think that'll fix it. Uh, Obviously, it's going to be big enough anyways. So what I'll do now is we're doing another problem, but in this case, the problem is everything else the same except now this force is equal to 50.0 newtons. That means all the drawings and stuff I did are fair game, but the 42s that I use are going to change to 50s. So I'm going to erase this 42 right here. And I am going to erase this 42. And of course, that's obviously going to give me a different answer for f sub x and f sub y. So I'm going to erase those. And we'll just work through them like we did before. I'm going to say also that it's not much point in using a lot of this stuff that I did down here at the bottom. So it's probably just best if I erase all this. And that's what I'm going to do. So did anybody have any questions on the previous problem before I go on with doing a repeat of that with slightly different numbers? I'll turn it back to that page just to be certain. Anybody have any questions on this? Okay, it seems like we understand it despite my screw up. So let's look at this. It says, what is the acceleration? And we're assuming that FP is large enough that the static coefficient of friction has been exceeded, just like we did last time. I've drawn the forces here. You can see I have, for instance, the I have the normal force, which is perpendicular to the surface and obviously points upward. I've got the weight, which is mg, which is 147 newtons because that's 15.0 kilograms times 9.8. I've got the kinetic coefficient of friction. And of course, the formula for the kinetic coefficient of friction is F kinetic is equal to mu kinetic times F normal. And I have the FP force, which I'm going to write right here. FP is equal to 50.0 newtons, like that one. And now I need to compute the new x and y component. So I'm going to erase these values and we can move along. Notice the 147 shouldn't change, so that shouldn't be a problem. Now, what we're going to have here in terms of sine, sine is opposite over hypotenuse. The opposite we can see is the y component, and that's why I put it there. And of course, the hypotenuse is 50.0 newtons. That means the y component is 50 times sine of 30. And that gives us 25.0 newtons. We also have that 50 times the cosine of 30 degrees is the x component, and that is 43.3. Yeah, that's 43.3. Making sure I rounded the proper way on the last digit. So now I can take the summation of the forces in the y direction equals mass times acceleration in the y direction. Again, this is a box that potentially can slide left and right. We do not expect it to dig into the concrete or jump off the concrete, and because of that, we expect the y coordinate of the box to not change. And since the y coordinate of the box doesn't change, that means the velocity is zero, but it also means since the velocity is zero and still zero, it means the acceleration is zero. So when I go to do this, I can go ahead and write the normal force is the upward one, so that's going to be positive. And then I have minus, or let's say plus, the y component of force, which is the 25.0 newtons. So that's going to be F normal plus 25.0 newtons minus 147 newtons is equal to zero, and that tells us that the normal force is 147 minus 25 newtons. So 147 minus 5 is 142, and minus 20 is is 122. So the normal force is 122 newtons. Now I can do the summation forces in the x direction equals mass times acceleration in the x direction. But again, that's the only acceleration in play here, so there's no need to actually continue writing it with a subscript. So I'm just going to go ahead and write it down. We have acting in the positive direction a force of 43.3 newtons. And then we would normally add another force. In this case, we've got the friction force, and it acts in the negative direction. So rather than writing plus and then a minus symbol or a negative symbol, I'm just going to write minus. And that's going to be mu kinetic times the normal force, and that all equals 15.0 kilograms times A. So if I plug in the zero point 0.3 minus 0.30 times the normal force, which we said was 122 newtons, that's equal to 15.0 kilograms times A. Then we get 43.3 newtons. Now I'm going to take the zero point 0.3 times 122, and that's 36.6, is equal to 15.0 kilograms times A. So A is obviously going to be 43.3 minus 36.6 gives me 6.7. And that's really all the sig figs we get from that. That's 6.7 newtons divided by 15.0 kilograms. And when I divide that by 15, I get 0.447 meters per second every second. And that is the acceleration this object would experience. Notice it came out positive. That is what you expect because positives to the right, that happens to be the force, the direction that the 43.3 Newton force is pointing, and the 43.3 Newton force exceeded the friction force. Exceeded the friction force. So that's exactly what we expected. Anybody have any questions on that? Also, notice, like I was doing all that work last time, showing you that when a force is lifting up on an object, then that tends to decrease the normal force that the object experiences from the surface it's sitting on. And additionally, when you put a force downward on an object, that tends to cause the normal force to increase. So, for instance, one thing you might know about in everyday life, or one thing you might use in everyday life going forward, if you happen to be a person that drives, for instance, a truck, the truck normally has an empty bed in the back and is a very light back end. However, essentially all vehicles, almost all vehicles in the United States, are rear-wheel drive. So if you're driving a rear-wheel drive truck, which has a light rear end, if you try to take off on an icy surface or a slippery surface, you might discover that you can't move because there's not enough friction between the tires and whatever road surface you're trying to ride on. So if you want to increase that friction, you should increase the normal force. To increase the normal force, what you want to do is load up the back of your truck. Of course, there's dangers in that. If you go throwing stuff in the back of your truck, all that stuff becomes projectiles in the event of a wreck. So that could be a problem, but it is generally a good idea. So, for instance, my dad, who had to, he worked for Dominion Power for 30 some years, and he was constantly driving in the snow. When you have to do that, he actually loaded up the back of his truck with cinder blocks. And that happened specifically because one night we were riding down City Park Road and just touched the brakes, and the truck just went in a spin like that. And then he went to take off, and it wouldn't take off either. So he went and got a bunch of cinder blocks and just put them in the back. And he actually got so many that it stacked in the that it sort of did a Tetris sort of thing in the back, so that if they moved, they really couldn't move forward, backwards, left, or right. They could only pop out in the event of a rollover or something like that. So it was a little bit safer, but that's something you can do. That also, of course, works if you're not getting traction while driving in the mud. In principle, you could put more weight in the back of the truck, be that, your wife or your husband or the people that are riding with you, just long enough for you to get enough traction to get out. Anybody have any questions on that? So let me show you another similar example. Let's say we're pushing a box. So this is going to be example. Whoa, there it goes again, switching to a entirely different pencil. So let's call this example. I think this is example five, right? Yeah, this is example five. And what we're going to have here, you can imagine this being a kid on a sled, or it can be just a uh, box sitting on a surface, like a concrete, let's say, Home Depot floor or something like that. I'm going to say the static coefficient of friction is 0.40, and I'm going to say the kinetic friction is equal to 0.20. Okay. And what I'm going to do is imagine a force applied to this like this. So this is a pushing force, F sub P is equal to, let's say, I want to start off kind of low. Let's say FP equals 50.0 newtons. And let's say this angle right here is 36.8 degrees. So really close to the critical 345 triangle angle. All right. Our question is, will it accelerate? Well, the box accelerate due to the 50.0 Newton force. Shawnee, your mom's calling me and she keeps calling me. Uh, so what I'm going to do is I'm going to solve this with a 50 Newton force, and since I made these numbers up, there's some chances the same thing happens that happened the last problem. So I'm going to reserve part B until after we solve it. Let's first off see if it will accelerate. So I'm going to do another free body diagram just like we did before. My free body diagram is like this. There's my y-axis. There's my x-axis. And I almost always use right and up as positive, but you don't have to. I'm going to draw the box as a little green blob right here. And we know its mass is 20 kilograms. We know the forces acting on it. And I promised you some time ago that I would give you some methods to make sure you don't miss any possible forces acting on anything. So I might do that here in a second. There's the weight, and the weight is equal to the mass times gravitational acceleration. And in this case, the mass is 20 kilograms, which is, of course, 2 times 10 kilograms. 2 times 9.8 we know is 19.6, so 20 times 9.8 is 196. So the weight is 196 newtons. We also have in the upward direction a normal force, therefore I'm drawing it blue, and that normal force is Fn. We do not yet know what that normal force is because we obviously are going to have some issues with regards to this force that's not acting parallel to the x-axis or to the y-axis. We also have a friction force that I know for a fact is acting in the negative direction, and it's clearly not zero. We don't necessarily know what it is, but it definitely cannot be zero because the force on the left is pushing the box forward, and therefore it's going to act. We also don't know whether this friction force is static or kinetic, so that's another thing to keep in mind. I'm just putting the F there. So now I'm going to take this force that's not aligned along either axis, and I'll draw it as some color other than red and blue. I've chosen obviously green, and I've chosen this angle to be 36.8 degrees, which again, I'm telling you is roughly the small angle from the 3, 4, 5 triangle. Now, I need to break that force into components parallel to the x-axis and parallel to the y-axis, so I'm going to use my trig functions again. And the sine of 36.8, and I think it was supposed to be 9, but either way, it doesn't matter too much. The sine of 36.8 is equal to, so some old horse, opposite over hypotenuse, and we can see the angle opposite, or excuse me, the side that's opposite the angle is in fact this red vector. That's the y component, and it's a negative one. The adjacent component, on the other hand, is in the positive x direction, so I'm going to draw that one blue. That means that one's going to be positive, and this red one's going to be negative. And I'll write it this way and write vertically downward for some reason because I just can't fit it in that space. But the sine is opposite over hypotenuse, so that is FP, oops, that is FP sub y over the hypotenuse, which is 50.0 newtons. And of course, since I chose 50.0 newtons, I know that the 345 triangle predicts that the 36.8 degree angle should be opposite the 3, or in this case, the 30 newton side. So I'm going to say that FP sub y is equal to negative 30.0 newtons. If I do that with my calculator, let's see what that comes up to be. 50 times sine 36.8 equals 29.95, which is essentially 30 newtons, and I've pushed the negative in there. Now I'm going to say this is 30.0 newtons like that. And now I'm going to do my cosine function. And of course, this one gives me Fp sub x over 50.0 newtons. That tells me that Fp sub x is actually positive. In this case, it should be 40.0 newtons. Again, I'll check it with my calculator just to make sure. 50 times cosine 36.8 degrees gives me 40.03, which is really about as close to 40 as we need, like that. So now I have all of these forces drawn. I can't figure out what the friction force is yet, and I can't figure out what the normal force is yet because I need to use Newton's second law to do that. So we'll start off with Newton's second law in the y direction. So the summation forces in the y direction equals mass times acceleration in the y direction. And for the same reason I've been saying 1,000 times, the acceleration in the y direction is 0. So in this case, I'm going to get the normal force Fn, which is clearly in the positive direction, so I write it down as a positive Fn. And then I see I have a vertical force acting downward that's therefore minus 30.0 newtons. And then I have the weight that is minus 196 newtons. Again, we're still adding, but I'm just not taking the time to write plus a negative sign. And of course, the right hand side is 0. So this ultimately tells me that the normal force, Fn, is 196 newtons plus 30 newtons. If I added 10 to 196, I get 206, and then 20 would be 216, and then 30 would be 226. So that's 226 newtons is the normal force. So we have that. Now I do the summation forces in the x direction equals mass times acceleration in the x direction. But again, no subscript necessary on the a. Now the forces in the x direction are, we clearly have a positive 40.0 Newton force. That is the x component of F sub p. And then we also have the friction force, which is just script F, because we don't yet know whether it's sufficient to overcome the static friction. And if it is, then it would be dealing with kinetic friction. But if it isn't, it would deal with static friction. So I'm just going to say 40 newtons minus F is equal to, this mass turned out to be 20.0 kilograms times A. So we have that equation. Now, what I need to figure out is how big is the maximum static friction. So F static max is equal to mu static times the normal force, which in this case, our static friction force is 0.40, or excuse me, our static coefficient of friction, not our friction force, is 0.40, and our normal force is 226 newtons. I haven't seen anybody correct me, so I'm assuming all my arithmetic and stuff is right. So I'm going to say zero point 0.4 times 226 gives me 90.4. So we can see right now that clearly the 40 newtons is not sufficient to overcome static friction, so there will be no acceleration. So no, the object, oops, will not accelerate because F static is too large. Okay. So for part B, Shawnee, your mom's calling again. Part B, we'll say, will it accelerate if FP is equal to, now I want to make sure I go quite a bit larger, or I definitely want to make sure I go more than 90 newtons for the horizontal component. If I multiplied it by the force by 50 by 2, that would give me 100 for the magnitude, but that would give me a component of 60 and 80, so still not enough. So in this case, doubling it's not good enough. I am going to instead go up to, let's say, 150. Will it accelerate if FP is 150 newtons? If so, what is A? So there's your part B, if you will. So the same problem happens all over again, only now the force that we drew in green is 150 newtons. So all we have to do to make this complete is do the recalculation of the FP sub x and the FP sub y. So what I'll do is look at my vector like this. This is 36.8 degrees. This is 150 newtons. Uh, and then, of course, I'll draw my axes just to make sure we know which direction is the positive x and which direction is the positive y. So there's my x direction. There's my y direction. Again, we're going to have a negative y component. And again, we're going to have a positive x component. Like that. So now that we have it, we can go ahead and say sine of 36.8 is equal to FP sub y over 150 newtons. Therefore, FP sub y is equal to, here I am forcing the negative. It's going to be basically 3 times 30. In this case, it's going to be negative 90 newtons for that one. And just double checking since I'm doing this arithmetic in my head. That gives me 89.85, which would be 89.9, pretty close to 90. I'm going to stick with the 90. That's close enough for me. I'm also going to do cosine 36.8 degrees is equal to FP sub x over 150 newtons. That means FP sub x is going to be, again, forcing the positive. It should be 3 times larger than the 40 newtons. In this case, it's 120 newtons, and the 0 is considered to be a significant figure. So now the mu, or the static coefficient, or excuse me, the static friction max is equal to mu static times F normal. And we've got to figure out what F normal is, but we can do that with the sum. There goes my pen changing again. Ugh. We can do that with the summation forces in the y direction equals mass times acceleration in the y direction, and that's equal to 0. In this case, we're going to see, looking back at the other diagram now, we have the normal force. Why does it keep doing that? We have the normal force minus, in this case, it's going to be 90.0 newtons because of the FP sub y, and then minus 196 newtons, and that's equal to 0, and that gives us a normal force that's equal to 196 plus 90 be 286. So this is 286 newtons. That means our static friction is 0.40 times 286 newtons. Now, hopefully we haven't done so much that we've made the friction force too large again, but there's a good probability that that happened, and I'd hate to see it, but hopefully I made it big enough. So 286, or carefully made it big enough. 286 times 0.40 gives us 114. Whoa, just barely. That's going to be 114 newtons. And technically, we really only have three sig figs or two sig figs on that, so that'd be roughly 110 newtons. But I'll just write it with an underline there. So now that I know that the X component, which is 120 newtons, that's the force that's pushing it, and the friction force is 114, which technically we should call 110 from a sig fig standpoint. I know it's big enough to do it. So now I can take the summation forces in the X direction equals mass times acceleration. In this case, it's going to be uh, the horizontal component of Fp, which is 120 newtons, minus, now in this case, the friction force was 114 newtons for static, but since this force 120 is slightly above that, then we're not going to have to deal with the static coefficient of friction. We're going to deal with the kinetic coefficient of friction because kinetic friction is going to be at play. That means the friction force is 0.20 times the normal force, which is 286 newtons. And all that is equal to 20.0 kilograms times A. So we should be able to figure out that the acceleration is, I'm going to take 120 minus, I'm going to put this in parentheses just to be careful. So zero point 0.2 times 286, close parentheses. That gives me 62.8 newtons for the left-hand side. And actually, that 8 is not a sig fig, so I'll underline it. And then all this is going to be divided by 20 kilograms, and that gives me acceleration of pi. 3.14 meters per second is the acceleration on this. So again, that's 3.14 meters per second every second for the acceleration of this block. Does anybody have any questions on that? All right, it's 7 o'clock. Let's go ahead and let you guys have a break. It's actually 7:06, so let's be back at 7:12. I'll be making announcements to let you know when we're close to that. You can go ahead and chat me your first and last name. Remember, if you're in the asynchronous class, go ahead and type async on the end of it, or zero or O01B, something like that. But go ahead and do that. But you're free to take a break, and like I said, you got about 6, 7 minutes left. I'm here, so you still can ask questions if you have any. Got about 2 more minutes, everybody. All right. Should be about time. Anybody need any more time, or are y'all ready to roll? I've got the chat open, so I should see that. I don't think I like the updated version of. Yeah, I definitely don't like the updated version of Zoom. It changes my chat to individual people, and it's kind of a pain in the butt to change back. Oh, I found a shortcut. Okay, so it's a little better. All right, looks like I got everybody's name down here. Very good. Thank you very much. All right, so we just finished doing that other problem, and remember for part B, which I had to make up with the numbers as I was going. Uh, in that case, we did find that the 120 newtons that was the x component of FP was greater than the maximum static friction, which is 114 newtons. Therefore, we were able to conclude in part B that it would accelerate, even though I left off the A off the end of the word accelerate, I mean the E off the end of the word accelerate. But then we went ahead and realizing that it exceeded the maximum static coefficient of friction, or maximum static friction force, we knew that the force that it would deal with friction wise would be the kinetic friction. Therefore, I did F equals ma using the kinetic friction, and I got 120 newtons minus zero point 0.2 times 286 is equal to 20 kilograms times A, and that gave us A was 3.14 meters per second every second, and of course that's only good to one decimal place because of sig fig rules. So, anybody have any questions on that? Anything that you didn't understand, or anything you would like me to explain better? All right. Well, that seems like a good thing. That sounds like y'all are sort of getting it. Now, the other part of this chapter, in addition to the friction, is of course there's a couple things. There's banked curves. There's rotational motion, or not rotational, but circular motion. So I'm going to go back to that first page and show you what that was. Okay. So that first page said, in an attempt to help you better understand centripetal acceleration and circular motion, I am asking that each of you complete the following exercise. So it says, consider the vector position function. So this is what a vector function of a position vector function looks like as a function of time. We have r, the vector, as a function of t, the time, is equal to capital R cosine 2 pi over t. T, by the way, that capital T that you see is what we'd call the period of rotation, or the period of oscillation or the period of the circular motion. So basically t is the amount of time that it's going to take for this r vector, which initially starts pointing to the right and it goes in a circle like this. And it keeps going in a circle for all time. But initially at t equals 0, it's pointing just to the right. And at t equal, for instance, 1 second, it's going to point straight up, or excuse me, at t equal, yeah, at t equal 1/4 of a period, which turns out to be 1 second, it'll point straight up. At t equal 1/2 of a period, which is 2 seconds, it's going to point to the left. At t equal 3 seconds, which is 3/4 of a period, it's going to point straight down. And at t equals 4 seconds, the period, it's going to point to the right again. Okay, so it's actually a position vector for an object going in a circle of radius r. And the period of that circular motion is 4.00 seconds, or symbolically just plain t. Now, why did I say 4.00 seconds? That's because the next line says, or if you are a bit uncomfortable with symbolic calculations, you may consider r of t equals 1.00 meters. In that case, we're saying the radius is 1 meter. Times the cosine of 2 pi over 4.00 seconds. So you see the period I did call 4.00 seconds, times time, close parentheses, I hat, plus 1.00 meters sine 2 pi over 4 seconds, t, close parentheses, j hat. And compute for part 1 r of 0, r of t over 8, r of t over 4, r of 3t over 8, r of t over 2, r of 5t over 8, r of 3t over 4, r of 7t over 8, and r of t. If you're not doing the symbolic version, you can use t equals 4 seconds. So that means, for instance, t over 8 is obviously 4 divided by 8, or 0.5 seconds. T over 4 is 4 divided by 4, or 1 second, so on and so forth. Okay. For part B, or for part 2, I want you to plot all of those vectors on a good sized graph. I'm going to show you an example of that in a second, but what you're going to do is put the tail of that vector, that r of t vector, you're going to put the tail of it at the origin for each of the 8 vectors that you're going to draw. And then they'll point in whatever direction the mathematics tells you. And then for part 3, I'm going to ask you to compute v of t, which is the derivative of r of t with respect to time, and a of t, which is the derivative of the velocity with respect to time. So in other words, you're going to take a derivative of this r of t function, and that'll give you the velocity, and then you're going to take a derivative of that v of t function, and that'll give you acceleration. And then in part 4, I ask you to compute the magnitude of r of t, the magnitude of v of t, and the magnitude of a of t. So that's giving you an idea. Let me show you what I mean by that, because I've started on it for you in this subsequent page. Remember, this will be here on the video, but also right after this class, I always post this to my Google Docs. It'll be in your 241 folder in Google Docs. You can download it if you need. Okay. You have access to that Google Docs by a link in the modules that says helpful documents and links in your Canvas page. So let me scroll over to the page where I've started working this out a little bit. There it is right there. This is another way that you might enjoy, in fact, writing the vector function. You don't have to actually write the I and t, the I and j hat, excuse me. You can actually put it like it's like a point. Remember when we talk about ordered pairs or ordered triples, it's a left parentheses, then x, comma, then the y, comma, and then the z, close parenthesis. Well, when you're dealing with a vector, you can do the same thing, but rather than writing I hat, j hat, and k hat, you can actually put it in an ordered pair or an ordered triple, but instead of using parentheses, you're going to use a less than symbol on the left side and a greater than symbol on the right hand. So this R of t is an exact replication of that, but using that new notation. So what I've done here is I've taken and evaluated for each time t exactly what the x component of that vector would be, x of m, and I'm saying x of m, but it's not really x of m like a function, it's x measured in meters. Just like the t is not t of s, it's t measured in seconds, and the y is y measured in meters. Again, symbolically. So at t equals 0 seconds, you know that the cosine of 0 is 1, so you get r. That's why I have a r under the x. You know that the sine of 0 is 0. That's why I have a 0 under the y. And therefore, the vector points to the point x comma 0, which is, in fact, this point right there. When I do t over 8, it points to root 2 r over 2, which is this point right here, in terms of the x component, but it's also root 2 over 2 times r, which points to this point right here for the y component. So this is square root of 2 over 2 times r right here, and this is square root of 2 over 2 times r here. And then when we go to t over 4, you can see at that point, when I plug in t over 4, the cosine becomes cosine of pi over 2. And of course, the cosine of pi over 2 is 0. That's why I have x equals 0 for this point. But when you plug it in pi t over 4 in here, then again you have pi over 2. And the sine of pi over 2 is 1, so I get just plain r there, and that's why the y component is r. Now, if you can guess or think ahead a little bit, I'm pretty sure you know exactly what it's going to look like. This will be the next one, and then 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 a repeat of the first one will be the last one. That's what you're supposed to do. Okay? Now, after that, I ask you to calculate v of t, which is equal to dr over dt. I'm going to show you how to do that rather quickly, and I'll use this notation rather than the I hat and j hat because it's pretty straightforward to do so. I'm just going to put that, I'm going to just put that for the left-hand side. Now, the derivative of cosine, r times cosine 2 pi over t times t, is, of course, the r is going to stay there. That's not going to change. I'm going to have to take the derivative of cosine, which is negative sine, and then I got to take the derivative of 2 pi over t times t, and I'm taking it with respect to the regular t. So I get 2 pi over t times r times negative cosine. Excuse me. When I took the derivative, it changed from cosine to negative sine. That's why the negative came out. And that's 2 pi over t times t. Similarly, when I take the derivative of the second term, that's going to become the derivative of sine is cosine. But again, I got to use the chain rule, so I've got to also take the derivative of 2 pi over t times t. So I'm going to get positive 2 pi over t r cosine 2 pi over t. So that's what the velocity function is going to look like. And you can now plug in those different times again. And what you should see is you're going to get a velocity that is that way. That's your v of t for t equals 0. And you're going to get another one. If you plot it at this end, you'll see it's perpendicular to that r of t. And another one here. And another one here, 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 and then a repeat. So that's what you're going to do. That's what your velocity as a function of time is going to get. Now, the other thing is you're going to take the derivative. You need to calculate a of t is equal to dv over dt. So you're going to complete that same operation I just did on r. You're going to complete it now on v, and that's enough for you to work on yourself. Now, the next part, as I told you before in this description, We've now talked about plotting all the vectors on a good sized graph. I've shown you how to compute v of t and a of t to some extent. Now we're going to compute the magnitude. So I want to show you what happens when you actually compute the magnitude. For starters, I'm going to tell you that the quantity, note, 2 pi over t is also equal to parenthesis, or no, I won't use parenthesis. It's equal to 2 pi times the frequency, which happens to equal omega, which is what we call the angular frequency. Okay, so if you need that, for instance, when you see 2 pi over t, you can replace that with a omega, which is like a curly w, a curly lowercase w. That would save you a lot of writing, and I highly recommend you do it. But the other thing is it makes it a lot easier. So now I'm going to show you how to compute a of t. I'm going to go ahead and give you the answer of what a of t is, even though I'm not necessarily working it out. Uh, what we're going to find is when I take the derivative of negative 2 pi over t times r sine, obviously the derivative of sine is going to be cosine. So we're going to get back to where we started and it's still going to be negative. So the answer is actually going to be r omega squared cosine, and there's a negative here, omega t, and a negative here as well, r omega squared sine of omega t. That's the actual answer that you're going to get when you do this, the derivative. So this is something for you to shoot for. But now what I'm going to do is show you how to calculate the magnitude of a of t. Notice you have to calculate the magnitude of r of t and you have to calculate the magnitude of v of t. I'm just showing you how to do the a of t. So the Pythagorean theorem works. This is an x component in here, and this is a y component in here. So those are perpendicular to each other. So all you got to do is square them, add their squares, and then take the square root. And of course, it's a magnitude, so it's got to be a positive square root. So I'm going to put the square root right here. Uh, when I square that, I get omega square, or excuse me, I get omega to the fourth r squared cosine squared omega t plus omega to the fourth r squared sine squared omega t. Notice the negatives, because you're squaring, just disappear. Notice also, really big trick here, the omega to the fourth r squared can be factored out because it's common to both terms, and then we get cosine squared omega t plus sine squared omega t. Can anybody tell me a useful trig identity? Anyone? Yes, it equals one. Very good, Samuel. And I think a couple other people were trying to say that. So yes, sine squared plus cosine squared is equal to one. So we end up getting the square root of omega to the fourth r squared. So I'm just going to call that r. Oops. I'm going to call that r omega squared. And that is actually the magnitude. Now, if you had worked out the magnitude of the velocity, what you would have discovered is that the magnitude of the velocity is v is equal to r omega. And that means, of course, that omega is equal to v over r, where I'm now just using plain v to represent the magnitude. Remember, you could also write, when you write a magnitude, you can just write it without the vector symbol, or you can write it in absolute value bars with the vector symbol. So if I plug this in here, I'm going to get r times v over r squared, which is v squared over r, and that's what we call the centripetal acceleration. Notice I'm saying centripetal. And notice also that you've now derived the formula for the centripetal acceleration, which is A equals V squared over R, but you could also see it's R times omega squared. That's another version of it, completely acceptable to use that. Notice also that the circle is taking place in the XY plane, and the acceleration is also in the XY plane, and then it points towards the center of the circle. If you were actually going to plot the acceleration vectors, let's say in green, then at zero, this little green vector would be A of zero. This little green vector would be A of t over 8, and so on and so forth. So that's what those different vectors are. And now we have an explanation of how we get our centripetal acceleration formula. So I'd like to show you another type of problem like that. It seems obvious that I'm not going to be able to get through chapter 6, so we're almost certainly going to, well, we're definitely going to put off the second online, or excuse me, the third online test for at least a couple more days. But just keep that in mind. And now I'm going to go ahead and work another example. And in this case, we're going to work an example uh, regarding centripetal acceleration, just so we can get you started on chapter 5 material. So, for instance, if you wish for a car, let's say, how much friction is required, and we'll say Fs equals question mark, for a 1,500 kilogram car to take a R equals 50.0 meter turn at 60 miles per hour if the curve is flat. And what I mean by that is a banked curve like we have at Daytona and various other raceways allows you to make a turn with zero friction. Of course, there's a problem with that. If you actually literally had zero friction, if you didn't go fast enough around that curve, you'd actually slide down it, which is another problem in itself. But in this case, we're going to treat it as a flat curve. So what I'm going to see is this is our car. So this is the car. It's making a curve of radius R equals 50.0 meters, and it's trying to make it at V equals 60 miles per hour. If I draw a free body diagram for this car, then you'll see a little bit more what I'm talking about. So I'm going to draw this as my x-axis. Actually, that came out really badly. This will be my x, positive x direction. This will be my positive y direction. What we have here is a weight acting downward, which is what I've been calling the red negative direction. I don't know what's going on with this, but it's really making my life a pain in the butt by undoing everything I do. So weight is equal to 1,500 kilograms, which I'm treating as 4 sig figs, times 9.80 meters per second every second. So 1,500 times 9.8 gives me 14,700 newtons. I also have a normal force, F normal, that in this case, because I don't have any other forces acting in the upward or downward direction, we can see that the summation forces in the y direction equals mass times acceleration in the y direction, and the acceleration in the y direction is equal to zero. From that, we can see that Fn minus 14,700 newtons is equal to zero, so the normal force is equal to 14,700 newtons. And we only have three sig figs. The 1500 gave us four, but the 9.8 only gave us three. So those are all the sig figs. Now, in addition to that, what's going to allow the car to maintain its curve radius is whether the car skids. So it's going around the curve, and friction between the bottom of the tires and the top of the road surface right below the bottom of the tires, that's a friction force, and that friction force is what's going to force the vehicle to go to the right, which is what it needs to do to make a turn. So that force right there is a blue force because it's in the positive x direction. And that force is friction, and it should be friction static because we don't want the tires skidding. Okay. So it turns out that the acceleration necessary here is A is equal to v squared over r, and it's got to point to the right because that's what we learned in that derivation that I was just showing you, is that the acceleration is perpendicular to the velocity and it points towards the center. That's why it's called centripetal. Pedal means is like it's traveling towards, and center means the center of the circle. So it's traveling towards the center of the circle, not to be confused with centrifugal, which, by the way, a centrifugal force is a fictional force. It doesn't really exist. It's more like if people talk about a centrifugal force, it's really more of the acceleration that's been written normally on the right hand side of Newton's second law. But somehow, if you pull it over to the left hand side, it all of a sudden looks like a force. It's not supposed to be there, it's just part of the acceleration. So we'll get to that a little bit more. But A equals V squared over R. V, by the way, is equal to 60 miles per hour. And I have a calculator that'll quickly tell me what that is. I should know it off the top of my head, but I am likely to make some kind of mistakes. So I'm going to say 60, and then I'm going to use my units to say speed, miles per hour, and I'm going to add to it 0 meters per second, and that automatically tells me it's 26.8 meters per second. So the acceleration that we're going to have is 26.8 meters per second. That quantity's got to be squared, and the radius, of course, is 50.0 meters. This is a pretty tight curve, so I suspect it's going to be a really unrealistic problem. 26.8 squared gives me 718.24. Now I'm going to divide that by 50, and that's going to give me 14.36, which is more sig figs than necessary, but that's 14.36 meters per second every second. So you can see that's about 140% the acceleration of gravity. So that's a pretty extensive acceleration. Now we can use Newton's second law. The summation forces in the x direction is equal to mass times acceleration in the x direction. But this is the only acceleration. So again, I'm going to drop that acceleration in the x direction and just call it A. But it doesn't matter because I'm not solving for A here. I'm trying to solve for the friction force. So what we have is the friction force, F static, is the only force pushing it to the right, and that has to supply all of the acceleration. Well, that has to supply the mass times acceleration, and the mass, of course, is 1,500 kilograms to 4 sig figs, and the acceleration is 14.36 meters per second every second. So if I take that 14.36 and multiply it by 1500, you can see the force is going to be ginormous. It's 2.15, let's say 155. Actually, it should be 1547, but it was at 4, so it made it a problem. And that's times 10 to the fourth. So that's a pretty significant force. So we can see now that the friction force required for the car to make that turn is basically 20,000 newtons. And if you divided that by 4, gives you roughly what the force is in pounds. That's 5,400 pounds basically. So that is a problem where we can actually calculate, for instance, the friction force necessary. I've got to show you some inclined plane problems and stuff like that. I've also got to show you another Atwood machine with the inclined plane, and I need to show you fuzzy dice. That's a typical example I work as well. I have plenty of examples of this stuff, but I just don't feel it's appropriate for me to skip so many examples in a chapter. That's why I'm just going to go ahead and say that we're clearly going to push the online test 3 back because I'm not going to get finished with chapter 5 and 6 in time to make that a reasonable date for the test 3. But either way, let me show you now that I have done this. I'm going to show you some other problems. But does anybody have any questions about how to do this particular problem? We've only got like 9 minutes. So what I want to show you is an inclined plane because that involves some work that we need to be able to do. And try to figure out where I am. Oh, there I am. Okay, gotcha. So let's go to the next page. So what is the acceleration? That went really badly. The acceleration experienced, well, let's say achieved because it fits better, by a 20.0 kilogram box resting on a frictionless surface inclined at 30.0 degrees above horizontal. Okay, so what we're going to do here is imagine this is our incline. This is 30.0 degrees. This is our box, and its mass is 20 kilograms. Okay. Now, I've got to draw a free body diagram to figure this stuff out. I will tell you that other than inclined banked curves, when you're actually solving an inclined banked curve like we're going to do next time for cars and centripetal acceleration and stuff like that, when you're doing those, you don't use a tilted coordinate system. But it turns out just about every time you're trying to solve an inclined plane problem, it's better to actually use a tilted coordinate system. So that's what I'm going to do here. My free body diagram is going to be on an inclined coordinate system. It looks like the box should be sliding down and to the left, so I'm going to call down and to the left the positive x or x prime coordinate axis, and this one the y prime coordinate axis. And specifically, I want to remind everybody that this is 30.0 30.0 degrees. Okay, now we have the mass sitting right here, and the forces acting on it are, of course, the force of gravity, which is the weight. And I have to draw that vertical because that's really what the way gravity acts. And therefore, I drew it straight down. And of course, it's W is equal to mg, which is 196 newtons for this case. But notice this right here makes a right triangle. Everybody see that right triangle? That's a right triangle. So that means if this angle is 30, this angle is going to be what? So this angle is 30. What must this angle be? Watching to see if anybody types it in the chat.
60.
Yeah, 60. Very good. Now, with that in mind, you know this whole angle right here is 90. So what's this angle? This whole angle's 60, but this whole angle's 90. So what's this angle? This is a very, very important part because this is something that comes back and back to you like just about every day for the whole 2 or 3 semester sequence, depending on which one you take. So again, right triangle requires this angle to be 60, but the fact that this and this are perpendicular tells you this angle's 90. So what is this angle? Yep, Hope said it right. That angle is 30 degrees. So I'm going to write in here that this angle is 30.0 degrees. That's a key to understanding. So when you have the inclined plane like this and you draw the weight vector down, the angle between the weight vector and the negative y-axis is the same as the incline angle. So that's something that I don't want you memorizing because I need you to work out the geometry, because sometimes when we give you an inclined plane, instead of us giving you this angle, we sometimes would give you this angle. If we give you this angle, then you can't just blindly say this is going to be that angle. So I need you to do that. So think about that geometry that I just did. Again, right triangle means this is 90 minus 30. And then right angle means this is 90. And then this being 90 minus 30 means this one must be 90 minus parentheses 90 minus 30, which gives you 60. Or excuse me, which gives you 30. Sorry about that. Now I'm going to realize that I'm going to have a negative x component, or excuse me, a negative y component, but a positive x component. So this vector can be represented, oops, that was not right. I pushed red and it didn't copy red. So the y component of this weight vector is this quantity right here. And the x component of this weight vector is this one right here. Notice that's another right triangle. And since that angle right here is 30, this side is given by cosine and this side is given by sine. So this one's going to be 196 newtons times the cosine of 30.0 degrees, which gives me 170 newtons. This side down here is 196 newtons times the sine of 30.0 degrees, which is 196 times sine 30, which is 98. Okay. So we also have another force, and that force is the normal force. and that acts this way. Notice the normal force on an inclined plane is not vertical. The normal force is normal. It's perpendicular to the surface it's on. So in this case, it's just normal. It's just perpendicular to the surface. Now, that shows us that the only force acting down the incline is this 98 Newton force here. Now, the other part allows us to figure out what the normal force is. Obviously, the normal force here is going to turn out to be 170. So that's something you've learned. Notice it's not the weight, it's not 196, it's 170 because that happens to be the y component of the weight. And that's the only other force in the y direction. So that's the one that's got to cancel out. Now, the summation of the forces in the x prime direction equals mass times acceleration in the x prime direction gives us 98.0 newtons being the only force pointing down. That's got to equal 20.0 kilograms times A. So A is equal to 98.0 newtons divided by 20.0 kilograms. Oop, I don't know why I wrote a 3 there. That was pretty weird. God darn it. And obviously, that is 4.9, or in this case, that's 2 would be 49 and 20 would be 4.9. So that's 4.90 meters per second, which by the way happens to be g sine the angle of the incline. So that is actually what causes things to slide down inclines. It's the component of weight that's parallel to the surface. And that turns out to be g sine theta. Okay? Now, that was the last thing I wanted to show you because with those things that I've given you so far, you can do a lot of Chapter 5 homeworks. I want you, of course, obviously to start on Chapter 5. I don't remember what I have Chapter 5 due date for on the homework, but obviously it's not going to be due this coming, since you guys meet on Tuesdays and Thursdays, it's not going to be due this coming Monday. It has to be due at least this coming Wednesday, but even then it's probably not going to be that. So I'm definitely going to adjust it. So watch out for those changes in dates. And you guys are free to go. Thank you for coming. I'll wait for the last person to leave in case anybody has any questions. And I may send you some stuff, or I may post some more videos this week, this weekend. I'm not sure. I have a lot going on this weekend and last and next as well, so I probably can't do much. But thanks for coming, everybody. Hopefully, you all chatted me your first and last name as I had previously recommended. But you're free to go, and thanks for coming.
I just had a quick question about the first test.
Yeah, Kaylee.
You posted it twice. Was I supposed to take it twice?
Yeah, I was going to talk to you about that. You took you took both versions. I even had to track down to see which one you took first. You never get to take it twice because in your case you actually got to see the almost the same identical test both times. But don't worry about it. I figured it was something with regards to me putting them up there and y'all not knowing what to do. But no, you don't have to take both of them. There was supposed to be one that was just using the Respondus Lockdown browser. That you can only take if you have a physical proctor, a person proctoring for you so that they can watch you and all that. The other, and it requires a password. The other one includes the webcam, and that's for if you're proctoring it yourself. I'm just going to take the higher of those two scores for you, which, by the way, you did good job. Or if I remember correctly, I think you did pretty good, so good job.
Thank
But
you.
either way, I'm going to take the higher of those two scores, but I'm also going to offer, I still haven't done it, but I'm going to offer a chance for everybody that wants to improve their first face-to-face test.
Okay.
So we'll clear that up more in the future.
Okay, thank you so much.
You're welcome, Kaylee. Have a good one.
You too.
How about you, David or Darius? Anybody have any questions? All right. Well, thank you for coming, and I'm going to go ahead and call it a day. We'll stop sharing. And remember, I will be changing those due dates, but thank you. Bye bye.